When we try to predict the arrival of artificial superintelligence, the technology industry defaults to a highly specific mental model. We imagine a massive, centralized, monolithic silicon brain processing the world all at once. But as we scale our current models, that architecture shatters. The expectation of a single, godlike intelligence assumes that cognitive power scales through isolation and density. If we look at the biological record of how intelligence actually evolves, the exact opposite is true. Researchers James Evans, Benjamin Bratton, and Blaise Aguirre-Yarkis recently formalized this critique. Their work points out a structural reality of evolution. Cognitive capability is plural, social, and relational. Intelligence scales by interacting with other intelligences. We are already seeing this biological principle play out in frontier AI development. The most advanced reasoning systems currently operating do not rely on a singular, dense core. They rely on combinatorial complexity, networks of specialized subsystems communicating with each other. Preparing for an intelligence explosion requires mapping a sprawling computational society, where capability is measured by the strength and diversity of the connections between nodes. To understand why this shift from single to plural architectures is happening, we have to look at the mechanics of inference compute. For a long time, the assumption was that you could improve a model's reasoning by giving a single processor more time and power to think. This chart maps the relationship between inference time and logical output. On the x-axis, we have the duration of compute, and on the y-axis, the rate of reasoning breakthroughs. Extending a single linear compute cycle yields initial gains, but it quickly hits a hard ceiling. Just thinking longer along one isolated pathway yields diminishing returns. The defining characteristic of current frontier reasoning models is that they are actively engineered to break through this exact inference ceiling. They are designed to bypass the plateau where linear processing stalls. Escaping that plateau does not require a higher volume of raw compute. It requires a topological shift in how the data is routed. Instead of pushing information down a single extended corridor, the compute must be layered and distributed during the inference phase. Overcoming the mechanical limits of inference means solitary linear processing has to be replaced. The math dictates a move towards simulated, multi-agent social interaction. We can see this exact pluralistic architecture operating right now inside DeepSeek R1. It serves as a working blueprint for how internal plurality drives advanced reasoning. When R1 is given a complex problem and extended inference time, it abandons singular pathways. Instead of one long chain of thought, the data stream breaks apart and routes into a multi-agent loop. The model essentially spins up an internal network topology that researchers call a society of thought. Inside this network, distinct operational nodes take on specialized roles. The first step in the loop is spontaneous generation. One node is dedicated entirely to proposing multiple, competing logic paths outward. Those paths immediately hit an internal adversarial node. The secondary function critiques the proposed logic, actively severing the branches that contain mathematical errors or logical fallacies. The surviving pathways then pass through verification nodes before finally reaching a reconciliation node. Here, the remaining valid logic strings are woven back together into a single, highly accurate output stream. When solving a highly complex physics or coding problem, the AI isn't executing an isolated calculation. It is simulating a rigorous social process of debate, critique, and consensus inside its own architecture. This pluralistic framework doesn't stop at the edge of the silicon processor. As the internal architecture becomes a multi-agent network, the way users interact with it scales outward in the exact same way. Human operators are moving from the periphery of the system into the reasoning loops themselves, acting as integrated components. This creates a hybrid actor, the human-AI centaur. It is a unified cluster where organic cognition and digital processing interlock. In a centaur structure, the human operator's job changes. You are no longer standing outside the machine engineering a prompt. You are embedded as an active, specialized node participating in the swarm. Because multiple agents, both human and algorithmic, are feeding into the same recursive loops, the network develops collective agency. The final output is generated by the interaction of the entire network. The system produces actions and conclusions that completely transcend the direct control or intent of any single participant in the loop. This shift to plural hybrid architecture introduces a level of decentralized agency that bypasses the internal logic of traditional one-to-one control models. This brings us to a severe engineering bottleneck. The current industry standard for safety and alignment is built entirely on simple dyadic structures. Reinforcement learning from human feedback, or RLHF, operates as a strict one-to-one relationship. A human evaluator reviews an output and sends a single directional reward signal back to the AI node to shape its behavior. That mechanism only functions mathematically if you assume you are aligning one monolithic model to one human baseline. When we inject centaur networks and internal societies of thought into this model, the architecture fails. With dozens of autonomous nodes interacting simultaneously, that single reward pathway begins to scramble, cross, and ultimately shatter. Dyadic alignment is mathematically incapable of processing collective agency. A single reward signal cannot trace, verify, or contain the asynchronous interactions happening across hundreds of embedded human and AI nodes. Attempting to apply a strict one-to-one alignment protocol to a sprawling, decentralized network creates massive vulnerabilities. It leaves the majority of the system's interactions completely unmonitored and unaligned. To safely scale machine intelligence, RLHF cannot be the primary tool. We must engineer a new topological layer of systemic control. The required architectural upgrade is a concept called institutional alignment. It scales safety by matching the complexity of the network it governs. Instead of relying on individual human feedback, institutional alignment implements digital protocols modeled directly on the mechanisms of real-world organizations and free markets. We govern autonomous nodes using market mechanics. By establishing bids, asks, and cryptographic ledgers, data is exchanged only after passing strict filters. Mapping organizational hierarchies directly onto the architecture, we assign specific auditor nodes to constantly monitor and verify clusters below them. These protocols enforce alignment at a systemic level. If a node begins hallucinating or acting maliciously, it isn't corrected by a human spotting the error. It is immediately isolated and corrected by the economic and structural rules of the network itself. True AI safety at scale isn't a matter of training perfect individual obedience. It requires building a resilient, market-driven infrastructure of checks and balances. When we pull back and view this complete architecture at a macro scale, the full scale of the intelligence explosion comes into view. The internal reasoning loops, human AI centaurs, and institutional market protocols fuse into a single functional ecosystem. Scaling intelligence means embracing this extreme, sprawling plurality. The sheer density of interactions is what produces higher-order cognition. The engineering constraint holding us back is the desire to build a perfectly aligned, solitary superbrain. The evidence shows that goal is an architectural dead end. Alignment research must pivot toward these digital societies to keep pace with the increasing complexity of the networks we are building. The next intelligence explosion takes the form of a combinatorial city, proving that in the future of artificial intelligence, no mind is an island.